Okay, yeah, thanks for inviting me. Okay, so really, this is just okay. Some time ago, I'd given a series of talks at TIFR about Maldacena and Zhiboedov, just sort of summarizing what they did and how it relates to follow-up work. So this lecture is sort of based on that. So we're just basically discussing theories with a slightly broken higher symmetry. Okay, of which the standard example are Chern Simons vector models, and the references, I guess, for this talk are okay, and okay, so these are these papers, which you can contact me if you want to know what they were. Okay, so the outline of the talk is okay, so in today's lecture, I'll try to give a complete overview, and in the next lecture, we can do details if people are interested, or we can skip the next lecture, either way. Okay, so basically, I'll briefly review how you can exactly solve a theory with higher spin symmetry, which is based on Maldacena and Zhiboedov's first paper. Okay. Then we'll move on to solving theories with a slightly broken higher spin symmetry, and of course there's two aspects of the solution. There's a spectrum of operators, and there's 3-point functions. And then I'll just talk a bit about open questions, because there's many things which haven't yet been done in this field. Okay. So any questions or comments so far? Okay. Okay, so the standard example of a theory with a slightly broken higher spin symmetry is N Chern Simons plus a single matter field in fundamental representation. So that's all really we will talk about in this lecture series, though the methods could be extended to handle several matter fields in a fundamental representation, but that's not yet been done. Okay. Okay, this single matter field could be either a boson or a fermion, and And of course, there's a story about a duality between these two, which I won't review at this point. Okay, so we can ask if we have matter in a fundamental representation, what are the gauge invariant operators that the theory contains? Okay, and we want to consider single trace operators, because these are the operators which dominate in the large n limit. So in large n, we consider quote unquote single trace operators, and these are operators such as psi bar I with something inside. Okay, or in the bosonic theory, okay, by contracting a single fundamental and anti-fundamental index. Okay, and one can argue that these theories are conformal, so that they transform in representation of the conformal group. So we can organize these single trace operators into representations of the conformal group. So in a theory of say, free bosons, we find that the conformal primaries are a scalar field which has spin 0 and delta 1 because of boson in 3 dimensions has dimension 1/2, and also a tower of operators that schematically take the following form with general S and delta equals S plus 1. So basically one primary operator for each spin, and the dimensions of each operator are delta equals S plus 1. Okay, in the fermionic case, we have a similar story, except here the scalar has dimension 2 because fermionic fields, Dirac fermions, have dimension 1, mass dimension 1, so the scalar has mass dimension 2, and then a tower of currents such as the following. Okay. Okay, and these operators and their descendants, which are just derivatives of these operators, are all the single trace operators in the theory. Okay. Okay, now if you look at the first two currents, for example, J1 is a conserved U1 current, and J2 is the stress tensor, which is also conserved. Okay, in the free theory, you can check, in fact, that all the currents of spin S greater than or equal to 1 are conserved. So okay, and this can also be seen as a consequence of the fact that these currents are in representations of the conformal group, and representations of conformal group are characterized by scaling, dimension, and spin, and those representations for which delta equals S plus 1 are short, and hence annihilated by P, which effectively means that they're conserved. Okay, so any questions or comments? Okay, so just for a bit of notation as I write down these currents, since they have So these are a set of conserved currents, one of each spin. Hence, they also are related to a symmetry, because conserved currents come from symmetries, and that symmetry is what we call higher spin symmetry. Okay. So I'll not write down the currents very explicitly, just when I do write them down, I just define a little bit of notation. So, instead of writing all the indices down, I will, sometimes use a null. It's convenient to use what's called a polarization tensor to write down the indices. If z is just a general vector, then when you take the derivatives with respect to z, j is automatically symmetric in the indices. But if we take z to be a null vector, and we take derivatives carefully, we can ensure that j is also traceless. Okay, so by taking z squared to be 0 and defining okay, if that's clear, by defining this sort of derivative operator which has these extra terms to subtract out the trace, then you can just recover the traceless symmetric current by taking these derivatives. Okay. So then we don't have to write all the indices. Okay, and since z is null, it's even simpler if we take z to be a particular null vector, which I take to be in the so-called minus direction, or the plus direction. So if I define, okay, if we work in Euclidean space and I define this following vector, then I'll take, which you can also write as x minus, and I take minus like this, and so in light cone coordinates, j has all minus indices, and we won't write them down. So okay, so then whenever I write js, it really means js with all the indices in the minus direction. Okay, so now we have these currents, and they generate a bunch of charges. Okay, and those charges I can define as okay, so if I take a slice of space which is perpendicular to x minus, I can integrate over that to get a charge. Okay, so I have a set of charges, and these charges act on currents and operators. So 3-point functions are conserved with respect to these charges in free theory. Okay, so we can, so this is essentially what we mean by higher spin symmetry. Okay, so the first question you can ask is, if we have a theory that has this tower of currents or charges, do we know it's necessarily a theory of free bosons or free fermions? Okay, I mean, here I constructed these starting from a free theory, but if we want to solve the theory in a model sort of independent way, the question is, does every theory which has this collection of current operators and charges, is it a free theory? Okay, so in the first paper by Maldacena and Zhiboedov, they argued that the answer is yes, and it has to be either theory of free bosons or free fermions. So I'll sketch the essential points of their argument. Okay, and then we'll generalize the case of what happens when we have an interacting theory when the slightly broken higher spin symmetry is, when the higher spin symmetry is slightly broken. Okay. So any questions about what we will do? Okay. Okay, so what we will I think that there should be a concise form, but our approach will almost be that we don't know what the algebra is. We'll just take it to be undetermined coefficients and fix them by consistency. Okay, but there may be. I can write fairly explicitly in free theory the action of Q on JS in terms of just numbers. So, and you can then try to package that more elegantly. Okay, so we can know its form mod fairly consistently. So just, yeah.
I was just asking whether, whether do you expect to be in unique algebra, or, maybe you can have many.
Okay, if we're assuming a unique stress tensor, then there are essentially two exact higher spin algebras, one for free bosons and one for free fermions, as far as I know. And in some sense, that's what we'll show, and they're pretty similar to each other. Okay. When you consider slightly broken theory, you can argue that there's some freedom, but
the gauge group doesn't enter at all in the discussion, doesn't color the higher spin algebra in any way, or?
Well, I'm assuming a single stress tensor, so in some sense there's no global symmetry in the free theory, and I'm just directly working with gauge invariant operators. It's true that it could be generalized to theories with more than one stress. So if you want to consider a supersymmetric theory, this analysis doesn't in itself apply. Okay. So we have these set of charges, and okay, the first question we can ask is, how do these charges act on these currents? Okay, so to do that, we first look what is the dimension and spin of this charge. So this minus will cancel out one of these other minuses, so this has spin s minus 1. Okay, just like the conserved charge for stress tensor is momentum, which has spin 1. Okay, and its dimension is also s minus 1, because this is s plus 1, and these kill two dimensions. So the dimension is s minus 1, and it's convenient to define a quantity called twist, which is the spin minus the scaling dimension. So qs has twist 0. Okay, so Qs has twist 0. Okay, these currents J, since delta is s plus 1, have twist 1. So Qs acting on Js prime also has to be twist 1, because it doesn't change the twist. So you can ask, what is the most general expression that could appear on the other side. Okay, so since this is twist 1, and if these are the only currents in theory, we expect it should also be has to be based on twist 1 operator on the other side. Okay, with some derivatives acting on it, because a derivative increases the spin by 1 and also the scaling dimension. I said also spin can be just thought of as the number of free minus indices. Okay. Okay, and then to match the spin, we know it's going to have to be S minus 1 minus S prime, S minus 1 plus S prime minus R, so that the spins on both sides match. And then there can be some constant. Okay, so in general, QS acting on JS prime is a sum of terms of this type. The upper limit is, of course, of this sum is S plus S prime minus 1. The lower limit you think is 0, but by consistency we can show the lower limit is not 0. So at present these are unknown coefficients, and our strategy will be just to fix them only using requirements of consistency. Okay, so a simple example of that is how do we show. Okay, so a simple example of that is this lower limit of this sum. So I claim, okay, suppose QS acting on a current Jx includes a term which is some derivative of current Jy, then you can argue that QS acting on Jy has to also include a term, perhaps with a different coefficient, acting on Jx. Okay, and the reason for that is if we consider the action of Q on the two-point function Jx, Jy, that is QS. Okay, and it has to equal 0. So if QSJX contains a JY term, then QSJY would have to contain a JX term to cancel it out. Okay. So using that, you can fix the lower limit, because the lower limit here sort of corresponds to an upper limit for Q acting on JR. And that's, so the lower limit is not 0, but R equals the max of 0. Okay. Okay, and these are essentially the sort of consistency arguments we'll continue to use. Okay, and C's are dimensionless, just numerical constants. If you want to know what the values of the C's are in free theory, you can use the fact you can define Q S, say, on psi to be d minus to the S minus 1 psi, and a similar relation for psi bar, maybe with some minus 1. Psi bar, and then using the expressions for currents, one can explicitly derive what the C's are in free theory. But okay, I mean, for the assumption, for the purpose, our purpose, we're simply assuming that the charges exist, and we want to show that if a higher spin charge exists, the theory is free. Okay. so again, any questions so far? Okay, so now, but to show that the theory is free, all we will, I mean, to the extent that we'll show it is we'll show that 3-point functions of these current operators are restricted to the values that you would get in free theory. Okay, so we'll just use the action of these charges to solve for the 3-point functions of the theory. Okay. Okay, so suppose we calculate a 3-point function of the 3 currents using conformal invariance. If you require the 3 currents to be exactly conserved and conformally invariant, one can show that there's three allowed forms for these currents for the 3-point function, which is the form you would get in a theory of a free boson. The form you would get in the theory of a free fermion, and an additional parity odd term, which also exists, and that's what arises at one loop in Chern Simons theory. Okay, so for the purpose of showing that a theory with a higher spin symmetry is free, we can consider these C's as unknown and these coefficients alpha, beta, and gamma as unknown. And we just solve them by consistency, and consistency means the action of this charge on the 3-point functions. Okay, so that's okay, which is and it turns out that, in fact, it's possible to do this because the action of Q's do not commute with conformal transformations. So for a single 3-point function, since that's a function of x, y, and x1, y, x2, and x3, this is actually a fairly large number of equations. So if you solve for the constraints implied by these equations, you can argue that these alphas all have to be the same and equal to, say, 1, or the betas all have to be the same, and the gammas have to be the same. And with a few tricks involving the 4-point functions, it comes out that C's, alphas, betas, and gammas all are fixed to be the values you get in free field theory. Okay, so is that clear, or? Okay, so again, just to repeat. Okay, the strategy is simply, we know JS1, JS2, JS3 is of that form, but we also require that Q acting on the 3-point function, is an exact symmetry. So this equation is equal to 0. Plugging those and these into here, we get a bunch of equations which relate the C's and the alphas and betas and gammas to each other. You analyze that set of equations carefully, and you can essentially show that the only solution is that of free field theory.
You have to use the conservation of,
Right. So
conservation laws of currents.
Right. So the way we use conservation law of currents is as follows: that if Q is exactly conserved, then Q acting on a 3-point function is 0, which what that means is Q, the commutator of Q JS1, 3-point function with this plus this equals 0. So this is the we translate the conservation equation into this well, at present we're right. So we have to show, of course, when the theory is not interacting, we want to show that gamma is 0. Okay, then very shortly we will extend it and show that gamma is non-zero, right? But to okay, but the procedure is similar. So if okay, so let me just. Okay, so maybe I'll give a sort of an example to illustrate this general idea more carefully, more explicitly. But just repeat the general idea is we know the allowed forms of the 3-point function in terms of these variables alpha, beta, and gamma. Okay, and we know the action of charges in terms of these variables C's, and we have this equation Q acting on this 3-point function is 0. Okay, so and we know the exact forms free fermion, free boson, and parity odd. So when we put this in, we get so for any choice of spins and a charge S, we get a large number of equations from any given equation, any given 3-point function. And it turns out those equations are enough by consistency to solve for the C's and the alphas, betas, and gammas. So if Q is a symmetry of the theory, if it's not, we will have to modify this in the slightly broken theory, but we'll see that it's so when it is a symmetry, this is what happens. In the slightly broken case, we modify this slightly, and we'll see it gets modified in a way that's you can handle. Okay. So if you want, I can go through the details of this, or I can just jump ahead to the non-conserved case if you're to the details or the non-conserved case. Well, I don't. Let me just give you a example. Okay, so in fact, I mean, I was assuming the existence of all these currents. You could say, suppose I assume the existence of just a single current, say J3. Does that imply the existence of another conserved current J4? Okay, so you can argue that it does via the following sort of argument. So if you ask, okay, we can write what's the most general action of Q3 on J2. It will have Okay, so if we're in the bosonic theory, it gives you, this total spin is 4, so you have 4 derivatives acting on J0 with some unknown coefficient plus 3 derivatives on J1. 2 derivatives on J2. 1 derivative on J3. And also a J4. Similarly, Q3 acting on J3 has to be okay, so we have these, these undetermined parameters. Okay, then there's a few things we can check. If we were to integrate this whole thing over the variables of J2, then these terms will drop out because they're derivatives, and we would just get a Q4 over here. But if you choose the right thing to integrate it by, this is just the momentum operator. So we want Q3 to commute with P, and that means alpha 4 has to vanish. Okay, so one way, I mean, that's one example of consistency. It tells you one guy vanishes. Okay, since Q3 will transform under conformal transformations, including rescaling, that means alpha 3 has to be non-zero. And then by that argument I told you earlier, that means beta 2 also has to be non-zero. Okay, so for example, we have these relations. Okay, so now we have these unknown coefficients, and we just write the equation with J. Okay, and now we specifically study this 3-point function, and we require it to be 0. So now studying the 3-point function is sort of a little tedious because you have the forms, but you can do it on Mathematica or whichever way you do, and you'll find that it's impossible to satisfy this equation unless beta 4 is non-zero. So that implies that if you have a conserved spin 3 current, you have to have the conserved spin 4 current. Okay? And perhaps it's not satisfying because I'm not explaining those steps, but they're just, at least as Maldacena and Zhiboedov do them, they're fairly just tedious steps which you can do if you know the explicit forms just on Mathematica. Okay, there's a few more comments. If you want to solve these equations, you can notice that, of course, the parity odd and parity even 3-point functions would have to separately solve these equations because either the equation is parity even or parity odd. And you can also check from the form of the free fermion and free boson that even the free boson and free fermion have to solve them separately. So by just acting on the 3-point functions and demanding consistency, you can show that all these alphas are equal. So you could have, say, alpha S1. Okay. Okay, and is this visible? Okay, but you can't show that, that only alpha is non-zero. So to show that the betas, and say you're in a theory which has a twist 1 scalar, then to show that betas and gamma are 0, you also have to study the charge conservation acting on 4-point functions. Okay, but once you do that, you can show that eta and gamma are 0, and the theory is essentially the theory of free bosons. So if there's no questions about this, I'll move on to the case of slightly broken higher spin symmetry. Okay. Okay. Okay, so we're interested in the case such as in Chern Simons series where the higher spin currents are not exactly conserved. Okay, so we can ask, okay, suppose this is, this current is not conserved. What are the possible terms that can appear on the other side of the non-conservation equation? Okay, so the first thing to notice is that what appears on the right-hand side has to be a conformal primary. Okay, that's because this is in a short representation in the free theory. If in the interacting theory it's in a long representation, the additional states that form the long representation are what come on the other side, and those have to be from an independent representation in the free theory. Okay, so what comes on this side is a conformal primary in the non-interacting theory. Okay, then we can ask, what can it be in terms of the j's? Okay, so to do that, we'll do some n counting. So let me use the normalization such that 2-point functions and 3-point functions are order n in the normalization. So first we can ask, is there any single trace sky that can appear on the right-hand side? So now this spin, say we're looking at divergence of J4, the spin is now 3. Whereas the mass dimension is 5 plus 1, which is 6. So it's a twist 3 operator. Okay, so there's no single trace twist 3 operator that we have. Okay, because in the free theory, so there's nothing that can appear at the single trace level. At the multi-trace level, you can construct a twist 3 operator, for instance, using one derivative, J0 and J2, if we're, say, in the free fermionic theory, because J0 has twist 2 in the free fermionic theory, J2 has twist 1, and so that's twist 3, and a D with the minus direction in the minus does not increase the twist. And you keep a single D minus to match the total spin. Okay, and so there are some single trace terms you can write down. By demanding that it's a conformal primary, you can specify exactly how the derivative acts. So you have a term where the derivative acts like this, plus a term where the derivative acts like this. And by demanding that this is annihilated by k, the ratio of C1 and C0 is fixed. Okay, so in this way we can construct possible double trace operators that can appear on this side. Then there's also the possibility of triple trace operators. Okay, but so if you have three triple trace operators, for example, J1, 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 that can also appear on the side. Well, a single triple trace operator can also appear here. You can't have any product of 4 operators because that would have twist at least 4. And we want this to have twist 3. Okay, so the conclusion is that, is that the right-hand side of the conservation equation is a sum of double trace contributions plus a sum of triple trace contributions, and we can determine precisely their form using the fact that the currents have to be conformal primaries. Okay, so then the next thing we can ask is what are the values of C? I mean, what's the n dependence of C? So if I was to take a 2-point function here with JS1, JS2, okay, then on this side I get a term which is order n because 3-point functions we're normalizing to be n. And here, let's say I'm specifically looking at I want to know the coefficient of the double trace term involving JS1, JS2. So here I get a factor of n. On this side, if I calculate this, this 4-point function factorizes into 2 2-point functions, so I get an n squared. And that means C1 has to be order 1 by n. Okay, so C1 here is order, well, let's call it C1 by n. So, okay, and similarly, you can argue that C2 has to be order 1 by n squared. Okay, because okay, so is there any questions or comments on this? Okay, so in a sense, we've seen that because we only have so many operators in the theory of the form JS, I mean of delta equals S plus 1, the way in which this equation the currents can be not conserved is fairly constrained. Okay, and in principle, these coefficients are suppressed by 1 over n. So now we can see what we can do with. So now we can say if we can use this to solve for the 3-point functions of the theory directly. Okay. Okay, so the first thing. Okay, so now we can. Okay, so now the task is to solve for the 3-point function. So earlier we solved using these equations. Now what do we do when the current is not conserved? Okay, so we can still define QS. Okay, as this charge, but it's not quite conserved. Okay, then. Well, okay, maybe let me start with a different relation. Okay, so what we do is we consider this 4-point function, which is divergence of Js with Js1, Js2, Js3. Okay, and now we integrate this. We carry out a volume integral integrating this around a region which around as okay in a volume which excludes the points x1, x2, and x3. Okay, by the divergence theorem, you can replace this by a surface term, a flux over the surface here, which in turn is nothing more than QS acting on JS1. So I claim this is the modified equation when the Q's are not exactly conserved. Okay, and this is just, I mean, this is of course familiar from 2D CFT, where you integrate around circles to get commutators of charges. So we can do the volume integral of d mu j mu x with this 3-point function, and that's equal to QS, the commutator of QS, if this region of integration is chosen appropriately. If you can take the region of integration to be, say the points are x1. We can take them to be, light-like sort of slabs like this. So once you use the divergence theorem, what you get is literally the commutator of Q acting on JS1, JS2, JS3 when this is a time-ordered correlation function. Okay, so then what we have is we have a situation similar to what we had earlier, where Q's acting on the J's were supposed to be 0, only in this case, sometimes the right-hand side of the equation will be non-zero. It'll only be non-zero if one of these S's, S1, S2, S3, match a current that appears on the right-hand side of the non-conservation equation. Because otherwise this... Okay, because when you replace this by the non-conservation equation, you would get... Okay. Okay, so are there any questions about this setup, or? Okay, so let's just to be specific, let's consider the case of J4. Okay, so the divergence of J4, okay, you can argue is something like okay, I'm not sure if the factor of it's 2/5 or 5/2, but okay. If you consider a theory with only even spins and you try to write down the most general form for divergence of J4, it just contains a single double trace contribution, which involves J0 and J2. So now suppose I want to act on a 3-point function with Q4. Okay, it will be non-zero, but the non-zero part will be related to the divergence of J4. And that non-zero part will be schematically of this form. Okay, where I inserted that in here. Okay, and this in turn will be, if one of these is either 2 or 0, I can factorize this into a product of 2-point functions and 3-point functions. Okay, otherwise, if neither of these match, then this would be just a single 5-point function, which would be order n, and that would not count. So if we want to, so this could factorize, say, into J0, JS1, JS3 if S1 is equal to 0. And on the other side, we have the same combination of 3-point functions that we had earlier. Okay, so now the situation is very similar to what we had previously, except for that these conservation equations are not equal to 0. There's equal to a source, which is sort of a product of 2-point and 3-point functions. Okay, so then the challenge is just to solve these equations consistently to determine alpha, beta, and gamma. Okay, and again, it's just a tedious thing that one can work out, but it works out, and the undetermined parameters you can take to be the coefficients of the non-conservation equations, which serve as coupling constants for the theory. Okay, so when you solve the equations subject to these additional source terms, you find again first that all these are equal, but now they're non-zero and they're equal, and you can just define them to be in terms of C naught, and you get a precise answer. Okay, one place I use the fact that n is large is we used, amongst other things, we used it for factorization.
That's the only place.
Right, we used it mainly in these places, for instance, in factorization. So if n was not large, yeah, so basically that's where we used it, yeah. Okay, so let me just state, exactly what Maldacena and Zhiboedov did. Okay, so in carrying out this work, Maldacena and Zhiboedov first, they assume the theory contains only even spin currents, just to simplify the calculations. Okay, and then separately, they considered a theory which has either a twist 2 scalar, which would be a theory of free fermionic, starting would be a quasi fermionic theory because psi bar psi has twist 2, and they considered a theory where the scalar has twist 1, which is quasi bosonic theory. Okay, in the theory where in the quasi fermionic theory, there's just, well, there's most general form for divergence of J4 is parameterized by one constant. Okay, and then they're able to determine all the other constants of the theory, that is the alpha, betas, and gammas, just in terms of that one constant, by solving equations such as this. Okay, that of course in particular implies that there's just a one parameter family of theories with a twist 2 scalar, okay, which is enough, I guess, to convince yourself that there's a duality between the critical bosonic theory, which has a twist 2 scalar, and the non-critical fermionic theory. The meaning of quasi fermionic is, okay, so in a theory of free fermions, so fermion in 3-dimension psi has dimension 1. So the scalar operator you construct from psi has dimension 2 and has hence twist 2, because 2 minus 0 is 2. Whereas in a bosonic theory, the scalar has dimension 1. So quasi fermionic just means the scalar operator is twist 2. Is that? Okay, and one can argue that the only consistent scalars operators will either have twist 2 or twist 1. And you can't have operators in like with twist 3/4 or something, although in principle they would be allowed, but there are other consistency. Okay, so since you've confined that the entire 3-point functions parameterized by a single parameter, that's sort of enough to tell you that critical bosonic theory and the fermionic theory are dual to each other under strong coupling, because you have initially 2 theories, but there's only, in the model independent solution, there's only a 1 parameter family of theories, so those 2 theories have to be equivalent somehow. Okay, they also considered the quasi bosonic theory with only even spin currents. Okay, in this case, okay, you have some double trace terms. I mean, a single double trace term, which I won't write down, but there's also the possibility of triple trace couplings, of a triple trace term in the anomalous divergence condition, because now J0 has, since J0 has twist 1, a product of 3 J0s will have twist 3, and then with, say, a few derivatives sprinkled in, you can match the spins. Whereas there's no possibility of a triple trace guy appearing here. There's also another triple trace involving 2 J0s and a J2. Okay, so then when you solve for the consistent, when you try to solve these corresponding equations, you find that there's in principle there's 2 parameters. One is A0 and A1, and A1 and A0 are both independent. A0 again corresponds to the Chern Simons coupling n by k, whereas A1 gives you the classically marginal phi to the 6th coupling, which arises in the bosonic theory. Okay, so in the quasi bosonic theory, you can also count the total number of parameters, and you find the extra triple trace coupling gives you rise to a new parameter. So are there any questions about that? Okay, so of course, so one of the assumptions Maldacena and Zhiboedov have made was that they consider only even spins. Okay, but it's straightforward in principle to extend their analysis to consider odd as well as even spins. And when you consider odd spins, that means you have a J1. So it's possible to add an additional coupling of the following form, an additional triple trace coupling in the Quasi Fermionic theory. Okay, and it appears that that coupling, I mean, so far it appears to me that this coupling is independent. So it suggests that you have an additional parameter of solutions when you include odd spins. And that additional parameter could be, you can imagine, gauging the U1 current, the U1 symmetry, and coupling it to a second Chern Simons field. Okay, which gives you an additional classically marginal parameter. Okay, so that's one thing which I'm studying is to, if you extend the analysis to theories with odd spins, you may get, there's a few more terms that can appear on the non-conservation equation, and each term that appears in the non-conservation equation has a chance of being an independent parameter, specifying the allowed the number of different coupling constants you can have. Okay, and in principle you might get, you get at least an additional triple trace term. Okay, so that's one extension which is in progress. So there's also several other terms you can appear here, but they appear to be not independent. So it appears you also get an additional term from J1, J1, J1 here, but that's it. You have additional marginal coupling. Not necessarily fixed points, because that additional parameter can take on any value. But the family of theories with a slightly broken higher spin symmetry would be parameterized instead of by one parameter, but by two parameters. Okay, and that other, you can ask physically, how would that, in a Lagrangian description, how would that other parameter arise? And the guess is, if you take your U1 current, that was there, it was first just a global U1 current, but you can couple it to a Chern Simons gauge field. Okay, and it'll still be a conformal field theory, and that would give rise to an additional, the strength of that extra second Chern Simons field would be the extra parameter. Maybe there's some other way of thinking about it as well, but. Okay, so that's one extension, is to extend this analysis to theories with odd spins. A third extension is they also assumed, in all these analyses, we assume there's a unique stress tensor when the theory is free even, but if you want to consider supersymmetric theory, then there will be, at least in the free theory, there will be more than one stress tensor, though in the interacting theory, they'll have to combine so that only one is conserved, probably. So you can systematically try to redo this analysis where there's say two stress tensors and maybe spin 1/2 currents to solve, for supersymmetric theories with a slightly broken higher spin symmetry. Okay, and then you can go all the way with more and more supersymmetry to try to, I don't think at present people don't know the 3-point functions in ABJ theory. But in principle, since that's a theory with slightly broken higher spin symmetry, you can use these methods to derive the 3-point functions to all orders in lambda for the n equals 6 vector models. Yeah. Okay, yeah. So in fact, another thing is yes. So in the limit m much less than n. Right. So in fact, for generalizing to m much less than n, it's also possible that this analysis is slightly different. But you expect, morally speaking, in the limit m much less than n, a slight variation of this method should go through. Okay, I mean to work out exactly it's a little different because then here you might still call it a single trace operator, but it's just that it's glued together by an M index instead of an N index. So there's some slight things to work out, but morally speaking, the method should work for that case if the technicalities can be overcome.
The statement that there are all the conformal primaries are still currents in ABJ theory? It's not true, right?
No, but when M is much less than N. I mean, there's super partners and stuff of these. So before we consider that, you might consider just N equals 1 supersymmetry, a vector model with N equals 1 or N equals 2 supersymmetry first. Okay, so there in that sense there's some more currents which add to the complication, but the point is, if you add just a few currents, you can still work this out. It's just a little bit more complicated. So even say you want to solve Chern Simons coupled to a boson and fermion, then this analysis doesn't apply, but modifying it so that it does apply is doable in principle, it seems. Well, which theory say?
Boson and fermion.
Okay, so first you have the bosonic tower of J0, J1, J2. You have the fermionic tower, J0, J1, J2. Then you can probably take, since boson and fermion both will have fundamental and anti-fundamental index, you get these spin 1/2 currents. And maybe you get 2 towers or 1 tower of spin 1/2 currents, but I think that's it. So 3 or 4 times as many currents as you have here. But twice as many integer spin currents and also half integer spin currents. So that's answering the question, I guess.
More general question, which is that like this violation of these higher spin currents and so on.
Right.
How much do we understand them from the side of gravity?
From Vasilyev theory. Okay, so one philosophy you can take is simply to calculate the. Okay, so for example, if I was to take. So I mean, if you just want to calculate a 3-point function in gravity, if you take the right 3-point function, then that will map to 2-point function, so that would not be conserved. So if you find this given structure for J0, J2, J4, that would show that the currents are not conserved, are approximately conserved in the gravity theory. So I think recently, Skvortsov and Vasilyev managed to calculate these when one of the spins is 0 in Vasilyev theory, and they had to, I think, change the equation slightly of Vasilyev theory. But okay, so it's
modifying Vasilyev theory by trying to
match the right forms of the 3-point functions, is what you're asking.
Classify the deformations away from Vasilyev theory, and one derive this equation.
It's not really a deformation.
Away from higher symmetry. Higher symmetry. Is there some systematic way to derive these equations?
I would not call it. No, I think they just literally changed the actual equation of Vasilyev theory, even for free theories. I mean, so ultimately you get this by changing boundary conditions, and considering Vasilyev theory with a phase. So it's not really that you modify Vasilyev theory to get non-conservation. It's still somehow built in if you consider parity violating Vasilyev theory. So we.
The boundary condition, and then you calculate quantum corrections.
No, we don't. I think the same way you will calculate a 3-point function, a parity even 3-point function, you can calculate the parity odd 3-point function. You have the conjectured dual to Chern Simons theory with vector matter, and you can calculate 3-point functions in that dual. Some parity odd 3-point functions have been calculated, which agree. Others have not yet been calculated, but can be calculated in principle. I don't know if we directly calculate a divergence of a current in Vasiliev theory, or you just calculate 3-point functions, and from there.
Maybe can you calculate the mass of the gauge fields?
The 1/n masses of the gauge fields. I don't know if I don't think that's not yet, of course, been calculated. And you can draw the Witten diagrams you would need in order to calculate them. But it could be tried in principle, yeah. Okay, so maybe we'll just end this. Yeah. If you're in lower dimensions, the higher spin symmetry is less constraining. Because like 2D CFT, it would be harder to do this because it's less constraining. But in higher dimensions, it should be more constraining or equally constraining. Okay, and I mean, maybe for exact higher spin symmetry, it may have been done in higher dimensions, but I don't think the slightly broken case has been done in higher dimensions. So in principle, it could be interesting to see what you get, yeah. For free theory, or no, but you see, I mean, Lagrangian, I don't have a non-supersymmetric Lagrangian that gives me a small, that gives me a small breaking of it. That's conformally invariant. Okay, so I mean, you can still try to do the model independent way of seeing what could you get. But also in this case, you can argue that the 3-point functions which appear here have to be parity odd. So if parity odd 3-point functions did not exist, this story would not be consistent. Okay, so I'm tempted to think that it's the slightly broken case will only work in odd dimensions.
So effectively, that it may be possible that there is no slightly broken higher spin symmetry in 4 dimensions.
I mean, of course, subject here, the setup stops supersymmetry from the beginning because you have just one stress tensor when the theory is non-interacting. So if you have again one stress tensor and it's non-interacting, the guess is you will not have any slightly broken higher spin symmetry. If you have a supersymmetric theory, it may be possible. So but this is the guess. It's not a claim so much, but it's expectation. Yeah, I don't know if there exists any candidate tools in 5-dimensional Vasiliev theory that I'm not also sure what the 5D Vasiliev theories are. Yeah.